Thank you very much, David, and thank you to everyone at Monash for hosting me for the year, and especially thank all of you for showing up tonight instead of sitting at home watching the Olympics, which is probably what I would have been doing if I hadn't been here. It's really a great pleasure for me to be able to talk to you tonight. If I wanted to give you one... well, we've already had the first technical fail. Oh, and it's a big one. Yeah, no. No, we've got full-on fail.
There we go. The universe is okay though. We've got a crash.
Yeah. No, it doesn't. No, it's okay. It's all good. It did not like that, but I'm going to try it again anyways and live on the edge. That was a schoolboy error. No, it does not like that thing. Okay, here we go. I'm going to have to do it manually.
An extra class.
Yes, that's right. We've lost a couple of minutes. Okay, thank you, David. Okay, what are my goals tonight? I guess I've got three of them. And the first one is to try to, if not convince you, at least to show you that there are real and powerful synergies between the sorts of things that I'm showing you here on the left. This is a simulated volume of the universe showing this filamentary structure, and I'll come back to how that actually forms in a few minutes. And I've zoomed in on just one particular little knot down in the center of that where there's something that, to first order looks like our Milky Way Galaxy. And there's certain computational tools that we use to make these sorts of things, whether it's a universe or whether it's an individual galaxy. And the tools that we use to build these universes and galaxies are not dissimilar to the tools that we use to, say, model climate change, climate science, whether it's blood flow through artificial hearts, aerospace engineering, automotive engineering, oceanography, geoscience. There are real strong links between the two, and I'll try to draw those links out as I go through. Second, so that was my first task. The second task is to convince you, again, or at least show you, that at least, again, roughly, to first order, that all of the computational astrophysics that I'm going to be showing you over the next sort of 40 minutes or so really are driven by two basic concepts that are covered in sort of years, roughly, say, 4 through 8 in this part of the science curriculum in Australia. And basically, everything I'm going to be showing, at least all the computational astrophysics that I'm going to be doing, is tied up in just these two things, gravity and the laws of fluids. Those are basically the only physics I'm going to be talking about tonight, and all of the simulations that I'm going to be showing you are based upon those two, as I say, years 4 to 8 concepts within the curriculum. Those are the two things to bear in mind, gravity and viscosity. And when I say viscosity of a fluid, I just mean the thickness. Something like oil has a higher viscosity than something like water. And that's really the only scientific concepts I'm going to be drawing upon throughout all the things that I show you. And third, I'm not going to be spending a lot of time stepping through each of these equations one by one. All I want to do is give you just a feel, depending on how the time goes, on how we take these, at first glance, horrific-looking equations and all of the jargon associated with those sorts of equations, how we turn those equations into computer code, such as that on the left, and then put those, install them on a supercomputer, run them for days, months, years, however long you want them to run, in order to get things that, at the end of the day, look something like this. We're trying to, this is the goal of computational astrophysics, is to understand these gloriously beautiful observations of different types of galaxies throughout the universe. And so I will try to step you through the process of going from those sort of horrific-looking equations to the simulated outcomes and how they compare at the end of the day with what you actually observe. Are we actually successful in recovering things that look like what we observe with our telescopes? So those are the primary goals. The way we do this, the way I'm going to be doing it, is using what we call a simulation. And so what is a simulation? We hear the word all the time. Normally you can recognize one when you see one. You just look at that and think, hey, this doesn't look like real life. This is a computer simulation of something. It just looks too beautiful. And, that would be the case. But ultimately you'd like to know, well, what are they exactly? You hear the word simulation mentioned all the time in many different fields. It's not just astrophysics, physics, biology, chemistry, many different fields. And so the answer to that question, what is a simulation, can be boiled down to this equation. There's only two equations that I'm actually going to show you. This is one of them. It doesn't have any numbers in it. But this is really what a simulation is. There's a product at the end of the day, a simulated product. And really, at its simplest level, this is all it is. There's just two components. There are the initial conditions. There's the initial setup. And then you add in your physics, and you let physics do what it's going to do, and you end up getting your system, your simulated product at the end of the day. Now, it's sweeping all of the complexities under the rug there, but really that's what it comes down to. Any sort of simulation is driven by your initial conditions, how you set things up initially, and then the physics that you apply to those initial conditions. Now, in reality, we don't usually have 100% perfect understanding of every aspect of the physics that's associated to a given problem. And so generally what that means is you need a little help to guide the physics along the way. So you'll hear me mention occasionally boundary conditions. So in an ideal world, you can imagine, say with that simulation on the left, if you set up your initial conditions correctly and just turn on physics, say gravity, and just let the thing run, it will, if you've captured the gravitational effects correctly, you should get something at the end of the day that looks like a nice galaxy. So that would be great, but what we find in reality, though, is that we're not capturing every little bit of physics along the way, and so we need a little help. We have some boundary conditions, and I'll give you some examples of how we use boundary conditions to help guide us to the right answer. But to first order, all you have to remember is that you have a simulation is a combination of initial conditions and physics. And so there's a little bit of technical jargon in there. And so it's good to use maybe a different analogy rather than that equation. So I'm going to use an analogy that everyone will understand. And that is, instead of thinking of simulations being initial conditions and physics, let's just think of cooking. So you have a food product, something at the end of the day, you cook something, you've got something on your plate. Well, it's a combination of ingredients and chemical reactions. That's really all cooking is. And so in this particular case, we've replaced initial conditions with ingredients. So in the case of bread, you've got yeast and flour and sugar, salt, water, etc. Those are the initial conditions for this final product of bread. By themselves, they just sort of sit there. You can sit there staring at them for as long as you like, but they're not going to change. That's what they are. That's what the initial conditions are. So you need to put in some physics. In this case, it's the chemical reactions. You mix them together, you introduce heat into the equation, and you get various chemical reactions occurring. In this particular case, you get something which is similar to fermentation. So the yeast basically eats the sugar, and that ends up releasing carbon dioxide, and that's what ultimately drives the dough to actually rise. It's a chemical reaction. That's all it is. That is the physics at play. And that's all that cooking is. When you have red cabbage and you toss that into a frying pan and it starts to change color, you're changing the acidity of it. You're going from an acid to, the longer you cook it, it becomes more and more basic, and it becomes an alkali. You can throw vinegar back in, and that will increase the acidity again. It's just basic chemical reactions. So your final product there is a combination of ingredients, initial conditions, and chemical reactions, the physics. So that's the analogy that I find useful to use. And so that's basically all I said. It's just a different way of thinking of what a simulation is. And if you wanted to, you could extend that analogy a little bit further and think of the tools that you use in cooking. The tool that you use is a oven, stovetop. For the computational astrophysics simulations, the tools that we use are just the computer, a supercomputer. So that's just a further extension of the analogy. So let's look at a few different simulations. This is a very, very simple one, just taking, say, a block of water and dropping it. Now you can imagine what's going to happen in your mind. This water is going to fall down, it's going to hit the ground, it's going to splash. And so, in this particular case, thinking of how I just described the simulation as a combination of initial conditions, physics, and potentially boundary conditions. So this dropping water block, well, what are the initial conditions? Well, I've just lifted some water up to the top. The physics that's at play, well, you've got the gravity, because you know this thing, when you let go of it, it's just going to drop. You've got the viscosity of the fluid, depends whether it's water or molasses or oil. The way it splashes around will be a little bit different. And we've got a boundary condition. In this case, it's actually a physical boundary. We've actually going to let this water drop into a container. And so, when you hit go, this is what you get. Looks kind of cool. But that is, by definition, what we call a simulation. And as I take you along the step from, say, dropping water to simulating the universe and galaxies, just remember those various, again, the building blocks, no matter what the sort of simulation that's at play, it always comes down to the initial conditions, the physics, and the boundary conditions. This is another similar one that it's kind of a cartoon of what happens when a dam breaks. On this case, well, you can't see the wall, but there's an invisible barrier which is supporting these two fluids on this side. They're just color-coded a little bit different because they're slightly different densities. It doesn't really matter. But there's an invisible barrier in this container which is holding it up. And so you instantaneously remove that container. So some of the initial conditions, well, we've got the water's being supported by this barrier. The physics is going to be very similar to the previous one, because I've just got fluid inside of a container. So I've got a boundary condition in this case, which is just a rectangular container. But you can extend it to more sophisticated containers and think of it as what happens when a dam bursts and the water flows into a valley, for example. So this is a sort of a first-order representation of what that looks like. And so you instantaneously sort of remove the barrier, and you see what happens. But again, you've got initial conditions, you've got physics, you've got boundary conditions. This is, again, a simulation. I'm going to show you a few more simulations before we move into the astrophysics ones, just because some of them are just kind of cool to see. This is one of the highest resolution industrial simulations that's been done using a hydrodynamics code similar to what I'll be showing you in an astrophysical context, showing you what happens when a large wave splashes across an oil rig. Again, there's initial conditions and physics at play. So you can go beyond just those simple fluid examples that I've just showed you to many other applications where simulations come into play, even before I get into astrophysics. So that includes anything ranging from, say, explosive welding, if you're trying to weld two metals together that don't naturally want to weld together. In this case, this is aluminum, and I think I can't even read anymore what it is. But yeah, so stainless steel and aluminum. So they don't normally want to weld together in a traditional way. So the way you do that is you put two plates together, put some TNT, some explosive stuff on the top, and you ignite the explosive material, and it pushes the material across at supersonic speed, and it ends up fusing together. So this explosive welding is used for whenever you need to weld huge pieces of material, say that goes around cooling towers, on ships, submarines, anything where you need to weld huge pieces together. Explosive welding is used. And it's expensive to run the experiments, so what's done is people use simulations, again, very similar simulations to what I've been showing you, using the laws of fluids, to see what sort of properties of the properties that the welded material will have. You can have study the origin of, say, clouds. You can extend that to climate science as a whole. I just want to say a little bit about this particular simulation where the initial conditions were these. This is from the mid-60s in the UK and in Yorkshire, near Ferrybridge. There's 8 cooling towers here. There was a coal mining plant. These were constructed to withstand incredibly strong winds, and similar to what this simulation is showing here, there's a wind blowing in this direction. There's a barrier that's set up right there. And you can see the establishment of these vortices as the wind blasts through. Now this thing is untouched. The barrier is fine. It's happy. These things were similar to that barrier, can withstand that wind. But you get effectively these mini cyclones and tornadoes whipping along behind. And what happened when they built these things, they hadn't taken into account this effect of the vortexes, these mini cyclones. So they whipped themselves into a frenzy as the wind came through there and just tore down all the cooling towers. Just showing you that this was an era before computational simulations existed where they could actually experiment with this sort of thing. This is now part and parcel of designing bridges and buildings. People use exactly these sorts of hydrodynamical, fluid dynamic simulations to construct buildings and bridges and cooling towers. It shows you that there's a sort of real-world practical application to these laws of fluid dynamics that may not be appreciated if I just launch straight into an astrophysics talk. Also, for designing, like I said at the very beginning, designing artificial hearts and arterial blood flow simulations. This is just showing an artery with a valve opening and closing and showing the blood flow as it goes through. Again, there's initial conditions, there's physics, there are boundary conditions, just as there will be in the simulations that I show you. These are more practical ones. Again, on the design, aerospace engineering, automotive engineering, again, using the same laws of fluid dynamics that I'm going to be using in astrophysics. It's just showing the airflow over the car and the trailer. And I think the last one I want to say about simulations is that all the simulations I've shown you were driven by high-performance computers and the laws of fluid dynamics. But simulations come into play in many other areas, including, for example, epidemiology, modeling the spread of disease and disease control. These are, again, simulations, not in the, like I said, not in the hydrodynamical sense, but in the sense that there are initial conditions. There's an initial distribution of population. There's you introduce a trigger point or a ground zero where you introduce something. In this particular case, it's showing, if you're paying, it's probably hard to read, but this is showing the spread of an influenza epidemic where you introduced it into, I think it was Airdrie, Scotland is where it was introduced, and you see this, and the model takes into account the distribution of population, some basic information on how people move around the UK, as well as contagion rate, incubation periods, simple models about how you intervene and quarantine people. Down here shows you, on a larger scale, what happens when a worldwide pan-epidemic, where you introduce a trigger point it was in Jakarta, Indonesia. And if you look really carefully, you'll see these little white things flying out here. These are actually sort of the flight schedules around the world and making some assumptions on how the disease might spread through air traffic. And so in that case, this is one of the boundary conditions in some sense is the flight schedules, and you can see how it spreads around the world. As you watch this simulation, you'll realize there are reasons. Antarctic, Greenland, these seem to be pretty safe places to live. This one I just included because it's kind of cute. This is a epidemiological simulation, not showing the spread of a disease, but it's showing the spread of zombies, where they've introduced a zombie population into Peru. They've not taken into account how zombies might travel by planes and that, but you can see the zombie population working its way across the US at this point in time, and it's also working its way across Australia. We run this simulation through I have to look at the details of how they did this, but if you run it through to the very end, you will see at the last time step where the zombie-free zones will be. For some reason, Madagascar is untouched. Both Tasmania and New Zealand look pretty safe if there is a zombie outbreak. Greenland is also pretty good, and little islands off Alaska and northern Canada. So bear that in mind should this come up. So now let's move towards astrophysical simulations, and this is where my own work comes into play. So for modeling the universe, for modeling the galaxies like our Milky Way, it's effectively exactly the same as all the different types of simulations I just showed you. Like I said, we need initial conditions. We need to know what the appropriate physics to apply to those initial conditions are. And if we don't have a full, perfect understanding of all the physics, we need to impose some boundary conditions to help sort of guide us in the right direction. And so the first thing I'm going to start with is what is the actual physics that's involved. And where to actually begin? Well, I've chosen this particular point. This is this telescope is called the Leviathan of Parsonstown. It was built by William Parsons in the early to mid-19th century, so 1840s or so. For 70 years, at least up until the 2.5-meter Hooker telescope in 1915 or so came online. This was the largest telescope in the world. So for about 70 years, this was the largest telescope in the world. It's in Birr Castle in Ireland. Parsons, it's remarkable for a number of reasons. First off, it's just the sheer size. So it's about a 2-meter diameter. It's made out of speculum metal. It's copper alloy, kind of this metal that was used in medical instruments. The mirror weighs about 3 tons or so. It deformed heavily whenever it moved. It's so heavy, there's a very complicated array of pulleys and levers to actually move this thing around. It has been restored. You can actually visit it and see it. At the time, sort of in the mid to late 19th century, it was responsible, Parsons, looking through this thing, cataloged many thousands of galaxies, and at the time, 10% of the known galaxies were done by Parsons and his group, which is doubly remarkable if you know what the weather is like in Ireland. They estimate we've got, I think it was 60 clear nights a year, so we're getting basically one night per week or so to actually do observations, so it's quite remarkable. So Parsons built this to address, at the time, was a raging debate, or what we call the nebular hypothesis. And these fuzzy blobs that you could see on the sky, there was much debate as about whether these things were really clouds of dust, potentially forming planetary systems or stars, or whether if you had a big enough, powerful enough telescope, you'd be able to break up these clouds into individual stars. And the latter is what Parsons believed. He was having a big argument with John Herschel at the time, who believed that these really were gas clouds, and it didn't matter how big your telescope was, they would stay unresolved blobs of gas. So Parsons took this challenge on to try to resolve this. One of the first things he pointed at is what is now a very famous galaxy, and what we call M51, the Whirlpool Galaxy. And this is one of his great discoveries, was that, at least for some systems, he was able to resolve them into spiral arms and effectively into individual stars. It didn't stay just a fuzzy blob. He could see the spiral arms. He could see structure. He could resolve this thing when he had a big enough telescope. And that's his sketch, as I say, from 1845. And it doesn't look, wildly dissimilar to what, when you take a beautiful picture with Hubble Space Telescope looks like. So that was pretty good. At the time, it wasn't appreciated, but when we look back with hindsight, maybe his greater discovery was maybe not so much that they had these nebulae had spiral arms and they could be resolved as such. It's that even though he wouldn't have appreciated it at the time, these galaxies are not isolated islands. When you look at it, his sketch, you can see he's drawn in this satellite that is clearly interacting with the larger host Whirlpool Galaxy. It's pulling out this structure here, and you can see that quite clearly again in the Hubble Space Telescope one, telling us that galaxies, as I say, are not isolated. They evolve, they change, they interact, they undergo strong tidal interactions with neighbors, they accrete their neighbors, they cannibalize them, they merge, they grow. These things are, they're living, breathing entities. They're not isolated islands. And so we take that for granted now. It's fundamental to everything we know about how galaxies form, like our Milky Way. But at the time, clearly wouldn't have been appreciated. But it's all sort of wrapped up in that single drawing there, even though he might not have appreciated it. But if he had appreciated it and said, well, what does this actually mean? What is going to happen to this galaxy that is interacting with this neighbor? He would have been a bit stuck about how to actually model the interaction. Now, we can do this easily now. We can set up a set of 1 million or 1 billion individual particles to represent each galaxy, and we can throw them at each other in a supercomputer, and we can let the tidal forces come into play and shape the final product, and we can see what it would actually look like at the end. We call this an n-body simulation. We take something like a galaxy, we represent it with a certain number of particles, n particles. Now, those particles may be can represent stars, they can represent mysterious dark matter. I'll come back to that in just a second. But at the time, in 1845, it wasn't obviously wasn't an option for Parsons to do that. But the underlying physics was already in hand, had been known for a couple hundred years. We normally associate this with Isaac Newton, but it was first really quantified by French astronomer Ismail Bouli-Alvis. And it comes down to, this is the other equation that I was going to show you. Now it is what we call the inverse square law. And everything, all the simulations that, well, the computational astrophysics simulations I just showed you, this is really the only physics that is in there. I mean, there are lots of horrific-looking equations that I showed you at the beginning, but ultimately, this is all that's in there. And what is the inverse square law? Well, we take it for granted. It governs so much of what we do. We have, gravity, sound, light. If I turn off the microphone and just talk in a steady voice, for someone sitting in the front row, you hear a certain volume. Someone sitting in the back row, maybe 10 meters back, it's not going to be 10 times quieter. It's going to be 10 times 10 times quieter. So it'll be 100 times quieter. Similarly, if I had my flashlight and I turned it on to someone in the front row, and you measured how bright it was on your camera, and you did the same thing in the back row, you're 10 times further away, but it's not 10 times fainter. It's 10 times 10 fainter. So it's a factor of 100 fainter. Same thing with gravity. Gravity is what we call an inverse square law. As an object moves 10 times closer to another object, the strength of the gravitational attraction between them goes up, not a factor of 10, but a factor of 100. So that's what the inverse square law. And that's really all that goes into these sorts of simulations. So there may be millions, or there may be billions of particles in there, but they're really, at some level, they're just fancy tools for applying the inverse square law of gravity. So again, back to the original point, there really wasn't an option for Parsons in the mid-19th century, and so in terms of modeling, nothing really happened for about 100 years or so, until 1941, and that's when the first, what we call n-body simulation came out. Now, those of you who are aficionados of computers may wonder how the first n-body simulation was done in 1941, when computers actually didn't get invented till 7 years after that. And just as a brief aside to that first computer is called Baby. It was built at University of Manchester, and replica of it came online in 1948. Replica, you can go see it at the Museum of Science and Industry in Manchester, which is where I live. If you look at the numbers, I mean, first, the scale, it's really, really big. Secondly, if you compare the power of this computer back in 1948, it could do basically 1,000 things per second. Now, the typical chip that you have inside your laptop can be maybe 100 million times more powerful. So, looking down the road, that's what sort of 60 years of technological development has done. They're about 100 million times more powerful, just an individual chip sitting in your laptop. Similarly, the amount of memory that you can actually have on the chip is about 100 million times greater just on one of these little chips inside of this thing compared to this thing. But still. And of course, Australia also played a very important role in this. If you go to ScienceWorks, you can see this machine, CIRAC, which is, I think, the fourth computer built in the world, sort of a year later, 1949. But unlike Baby, which is this is a replica, there is no original components of Baby left around. CIRAC is the original one. It is the oldest original computer, actually. So if you're interested in the history of computer development, then head on down to ScienceWorks. So coming back to this, many of us in the field consider this the first computational galaxy formation paper, the first n-body simulation paper. This is from 1972, so only sort of 40 years ago. It's one of the most cited papers in all of science, not just astronomy. It has thousands and thousands. It's really the first application of these n-body techniques, where you have, in this case, what Toomre and Toomre did was they represented each galaxy with 120 particles. And then for every single particle, say for this particle right there, they wanted to figure out what is the force of gravity acting on that particle. Well, you would end up work out what is the force of gravity between that particle and that one. Then what is the force of gravity between that one and that one, that one and that one, that one and that one, that one and that one. You effectively just loop around all of them and figure out what the total force of gravity is acting on that particle. And then, depending on which direction the total acts upon, you move that particle a little bit based on the total amount of gravitational force that particle is feeling. And so you do that over all of the particles. And in this case, he had 2 galaxies, 120 particles per galaxy. So not huge numbers, but it was, you can see, even in that case, he's able to find initial conditions and throw these galaxies at each other to get something, in this case, that looks, this is the mice system, for those who know, get a system that looks kind of like the mice system. And through this paper, they went through many famous interacting galaxies and found the combinations that would lead you to simulation products that looked like what you saw in nature. And so that, as I say, one of the most cited papers in science. And we've now got problems again. Oh, there we go. A bit slow. If you take it, this is a paper, though, while the previous one has thousands upon thousands of citations, everyone in the field has read it. This one's got about 10 citations. Almost nobody has read it. It predates the other one by 6 years or so. This is one of the earliest I could actually find that uses an actual computer. It ran a low-resolution model, which had 16 particles, and then a high-resolution one, which is 25 particles. So it wasn't, not particularly ambitious by today's standards, but one of the first, what we call n-body simulations of the collapse of a globular cluster, a stellar cluster. But the first real one is this one in 1941. Like I said, 7 years before Baby came online in Manchester. This is an amazing paper that is genuinely an n-body simulation, but doesn't use a computer. It doesn't use gravity in any way, shape, or form. What it uses is the point that I made a few minutes ago, that light acts as an inverse square law, just like gravity acts as an inverse square law. So what he did was, his initial conditions was to set up on the floor of his lab, which is 4 meters by 5 meters, painted black, very dark, these 37 light bulbs laid out in this particular configuration to represent his spiral galaxy with these high-quality light bulbs, as shown here. And what he would do is he would put 2 of these down on the floor. They're about a meter across or so in diameter. And systematically go through, remove that light bulb, and then put this, think of it as just a CCD detector, similar as you might have in your camera, but at the time, this photocell and a galvanometer to measure the current. And he would put this photocell down at the position of every single light bulb, and then rotate the photocell in all directions, add up what the current is whenever it was pointed in every single direction, and after he had done that, he would have a total current that this thing had sensed, and that he could turn that into effectively the equivalent of what is the force of gravity based upon using the light intensity as a proxy for gravity. And he painstakingly would do this on the floor of the lab. He would have, he would try different setups, 2 of them on the floor, and then start rotating them in different directions and moving them towards each other, calculating the current going through the photocell at every single light bulb position, moving the light bulb according to the current that it felt. And at the end of his simulations, he had configurations that started to mix together. Sometimes they would have a bridge between them. They would have these tidal arms drawing out the backsides. These sorts of simulations, done in 1941 without a computer, look almost identical to what you would get when you do the exact same simulation with a real computer and putting in gravity instead of light intensity. But the conclusions, the results, and I won't go through them, about as these things get close to each other, this is as they pass each other for the first time is when the tidal arms get drawn out. All of his conclusions in 1941 using light bulbs hold up today. They're exactly the same sorts of conclusions that you would come to using a computer. It's just an amazing result. And as you jump forward 70 years or so, we've moved from having tens of light bulbs or tens of particles to represent our galaxy to now tens of millions, and people are pushing towards billions now. But again, what I want you to bear in mind in all of this is that ultimately, even if you've gone from tens of particles to millions and millions of particles, you're really just talking about, thus far, everything I've just shown you is just the inverse square law of gravity. And so that sort of covers the primary physics, gravity. The initial conditions, it depends on the scale of the problem. All of the ones I've just shown you, the initial conditions where you set up a disk already in place, and you threw two disks at each other, and you looked at what happened. So it was a small region of space. And if you wanted to simulate a large volume of the universe, well then that's not an appropriate set of initial conditions. You need a set of initial conditions that encompass sort of everything that you're trying to simulate. And so there are various analogies that you can draw. So that, again, there's not a single perfect set of initial conditions. It comes down to what you're trying to model. You wouldn't use a model of the initial conditions of the universe to do a simulation of how planets orbit around the solar system. That would just be complete overkill. So you just have to arrange your match your initial conditions to the actual problem that you're working on. And so for a lot of the cosmological simulations, the initial conditions are set by something that many of you in the audience will know, the cosmic microwave background. So I'm just going to spend very quickly whip through the universe in 30 seconds. You could have entire talks on this, but I'm not going to do them. You have a Big Bang, you've got little quantum fluctuations, you've got a rapid period of inflation. In those first few minutes is where you form the hydrogen and helium, all of the normal matter, what we call the baryonic matter in the universe is formed in those first few minutes. During this initial epoch, it's very hot. The electrons in these atoms don't want to stay attached to the hydrogen, to the protons, and so they're easily pulled off because it's just so hot. And so what happens is, as the universe is expanding, it's still very hot, but it's cooling as it's expanding. At the point when it's too hot for the electrons to reattach, all the photons are kind of trapped. The photons can't get out. The universe is just a fog. It's a screen. It continues to expand. It continues to cool. Eventually, it cools enough that electrons can reconnect onto the protons, and at that point, the photons can stream their way across the universe. We see that surface, what we call the surface of last scattering, as the cosmic microwave background, this afterglow of the Big Bang, which is, nowadays we see it as basically 3 degrees Kelvin, almost uniform, but it's not perfectly uniform. There are minute little differences in the temperature from point to point to point, which correspond to minute differences in what the density is in the universe. And those little density variations can trace back all the way to the quantum fluctuations of the Big Bang. These things are the seeds for galaxy formation. And I'm not going to step you through the gory details of what happens subsequently, but you do go through a phase of what we call the dark ages, where we're waiting for the first objects to actually turn on. This is partly what the Square Kilometer Array that Australia plays a leadership role in is designed to probe, that area where there's lots of gas floating around, but nothing is really formed yet. You form the first objects a few 100 million years later, and then you've got this process of clustering and merging and tidal interactions that eventually form the large galaxies that we see around us today. So that's the basic process. But the initial conditions really is that surface of last scattering. It's that cosmic microwave background is our initial conditions. This process of nucleosynthesis, then the creation of the chemical elements, in that first few minutes we are left with what is the building blocks of the universe. And like I said, this is what I just wanted to get back to very briefly. When we look at that pattern in the cosmic microwave background, if we look at the rotation rates of galaxies, if we look at how the number of galaxies evolves as a function of time, all of these give us a coherent picture where the vast majority of the matter is dark matter. We don't actually know what it is. You could have a whole talk on dark matter as well. We can't see it, but we can feel it. We can feel its gravitational effect. And then a smaller component of it is normal baryonic matter. This dark matter can be, even it dominates, like I said, it's 83% of the matter in the universe is tied up in this, even though we don't know exactly what it is, we can feel it, we know it's there. And it only interacts through the inverse square law. So the vast majority of the matter in the universe, you can basically just use that inverse square law that I've shown you. And when we do that, when we just plug in the initial conditions from the cosmic microwave background, and plus the inverse square law, this is the kind of the result that you get. This filamentary web-like structure with, at the knots, you get rich clusters of galaxies and individual galaxies. If you go through and do the statistics of what you get out of the simulation just using that basic physics, you get something that looks very much what you actually observe in nature. This is color-coded by density of galaxies. So they're in the local universe using, again, an Australian-led project, 2DF Galaxy Redshift Survey. And this filamentary structure that you see in the simulations is what you find in nature as well. So it's great. I mean, these sort of models do appear to work. When you do large-scale simulations, they do seem to work. And when you zoom in on smaller scales and look at individual galaxies rather than at university scale, universe scale, they seem to work reasonably well. I'll come back to that simulation just towards the end. But if you look at this simulation after 13 billion years of evolution, compare it with what you observe, simulated galaxies, much like the simulated universe, at least to first order, don't look too bad. The basic laws of physics that we've put in with our initial conditions seem to do a reasonable job. But there are some problems that it wouldn't be an interesting area of research if there wasn't unsolved problems, and there's a number of them. If you look more carefully at the simulations, this is one particular simulation that we had done, you've got this big bright spot in the middle, which is, let's call that our galaxy. But if you can notice there are lots of little knots all around, hundreds, thousands of them around this galaxy, little satellites. When you go out and look in nature, whether you look at our Milky Way or other nearby galaxies and start counting sort of the things that are around it, you don't find hundreds, thousands, or tens of thousands of these little satellites. You find a handful of them. And this is one of the problems which various people have come up with potential solutions, but we call this the substructure problem. We overproduce satellites compared to what you actually observe in nature. And the solution to this is to come full circle on where I started. The most likely solution is that it's not tied up in the 83% of the matter in the universe, which is that obeys the simple inverse square law. It's that other 17%. That's where all the interesting gory physics is. That's where the hydrodynamics comes into play. And that's to do simulations which get rid of that satellite problem and a number of other problems, we need the laws of fluid dynamics. And the way forward for this actually can be traced to this paper. One of the co-authors, Joe Monahan, is a professor here at Monash, one of the founders of this technique, smooth particle hydrodynamics. We think of fluids as fluids, not as little particles. But what Bob and Joe came up with was a nice way to take a fluid and think of it as individual particles and still obey the laws of fluid dynamics. And so all those simulations I showed you at the beginning, or even this particular simulation, which shows, oops, it did not work. No, well, that does show you a plane landing in water and showing you the pressure change in the water. You can start to see part of it there. But all of those simulations I showed you, this one here, use the exact same technique of smooth particle hydrodynamics, SPH, that Joe Monahan here at Monash came up with some 35 years ago or so. And this is what really has revolutionized our field. And just in sort of the last 5 minutes, I'll take you through where we stand in the field today. This is one of our first attempts to merge gas particles which obey not only the inverse square law, but they're also, the gas can be thought of as a fluid that feels viscosity. So there are other forces that the gas particles feel that the dark matter particles do not. In this particular simulation, these big blue ones are dark matter particles. They move around, they obey the inverse square law of gravity, but they don't do anything else. The green particles are gas. And the gas also feels gravity and moves around, but the gas can also be heated up, it can be cooled down. You can do interesting things to gas. You can convert the gas into stars as well, the stars that we actually observe with our telescopes. And so this was one of our first attempts to merge these two approaches by turning gas into a particle as well and having these particles work together in the simulation. So this was the hope when we started to think about putting together the laws of fluids with the inverse square law. This is what we wanted to get. These are what real galaxies look like. I mean, to first order, a galaxy like our Milky Way, it has a big disk. It's got a small bulge of light in the center. There's sort of nice spiral arms. That's what we wanted to get when we merged laws of fluids with the inverse square law of gravity. The first simulations that were done, this is what you got, which is, this is it looking at it edge on, and this is it looking down on it face on. So you can convince yourself that there is something of a disk there, but it's clearly doesn't really look like the Milky Way. So we're talking, this is sort of 20 years ago, one of the first attempts really to do it. And what we got was stubby, thick disks. They're more like a football than a bulge, really. And there's not really anything that looks like a spiral arm. And really, 15 to 20 years of hardware and software development certainly has helped things, but the fundamental mismatch between what I showed you in real galaxies and the simulated galaxies existed. There's a huge amount of light in the center. There's I haven't shown you the scale, but the disks are still quite stubby. Still doesn't really look like what I showed you. And this is what, just in the last couple of slides, I want to tell you what our solution has been over the last year to this problem. There was something of what we would call an energy crisis. What we needed to find was, when we put gas particles into the simulation, the gas had a tendency to flow its way down too easily into the center of the galaxy. So it would flow its way in, you would get more and more gas accumulating in the center, its density would increase, and then it would have a tendency to form stars in the center, and you'd get this huge amount of light forming in the center. We needed to find a way to heat up the gas to stop it from flowing freely down into the center. So we needed energy. And the source for all of this has turned out to be, for the simulations that we've been doing, is what we call supernovae. These are the end of a massive star, 10, 20, 50 times the mass of the sun. After a few tens of millions of years, it's burned up its fuel, it collapses, it explodes, it deposits a huge amount of energy into the surrounding gas. And each supernova, to put it into context, puts in the same amount of energy as, well, if anyone knows, it's the most powerful nuclear weapon ever detonated. It's a 50 megaton blast called the Tsar Bomba. So if you took a billion of those, that would be the equivalent of one supernova. And there's roughly about 1 billion supernova, say, in a galaxy like our Milky Way today. Every 100 years or so, you get a supernova. So you can start multiplying those things together, and you can see that's an enormous amount of energy to tap into. And that's the energy we needed to tap into to get things that looked like this at the end of the day. Nice, extended, rotating disks with spiral arms. And occasionally, if you recall from the simulation early on, you would see blasts as energy and supernovae were going off, and you would see the gas being blasted out of the system. So this is where we stand today. These are the observations of what spirals look like, similar to our Milky Way, and this is what our target has always been. And this is basically work that was just published, I guess, just last week, maybe it was 2 weeks ago or so. I think these are the best cosmological simulation, using the cosmic microwave background as the initial conditions, putting in the physics as best we can, tapping into all of that energy that the exploding stars are providing. We're able to finally get things. This is our simulated spiral galaxy. Again, they're not meant to be one-to-one matches, but the point I want you to take from that is that we're now getting things that are thin, that do have nice spiral arms, that match in almost any way that you want to do a comparison statistically between our simulations with the observations. We're getting really close to reality. I mean, they're not perfect. There's still an enormous amount to be done, but we're getting there. This is another way to look at it. There's 12 galaxies shown on here. Half of them are real, and half of them are fake. And I honestly don't even know which ones are the real ones and which ones are the fake ones, because my postdoc, Chris Brook, who did a lot of this work, could put it together. I mean, I guess I could go to Google Images and probably find which ones match up with which, but the point being, it's very difficult, you know, and like I said, I ran these simulations and I don't know which are the real ones and which are the fake ones. So where do we head from, where do we go now? You know, I think we're pretty close to, you know, maximizing, you know, we've really tapped into our computer resources almost as best we can. Our computer codes are developed probably as good as they're going to be right now. There's still a huge parameter space, though, that needs to be explored, and that's why there's an investment in a lot of these interesting facilities that are coming online. In particular, from my perspective, this European Space Agency Gaia mission, which is a satellite that will figure out the distances, velocities, exactly to exquisite accuracy to a billion stars. A large chunk of our Milky Way you'll have a perfect three-dimensional map with perfect velocities for a large number of them. I mean, if you supplement that with an amazing experiment that hopefully will be starting this year, I guess in 2013, at the Australian Astronomical Telescope, the AAT. This facility is called Hermes, which if you look carefully, you'll see there's many little fibers, and it can look at a whole bunch of stars at the same time, and it can split the light up with a prism for each of these stars to very high resolution, and you can measure the chemical elemental abundance patterns, how much carbon, how much nitrogen, how much oxygen, how much silicon are in all of these stars. They're not going to be able to do a billion of them, like the ESA satellite is going to do, but they're going to do a million of them. And doing this on a star-by-star basis within our Milky Way provides us with amazing boundary conditions for the simulations. That's really, you know, we've got a pretty good handle on the initial conditions. We're getting there on the physics. There's still stuff that's missing, but we need more boundary conditions to help us fill in the gaps in the physics. So I think that is probably, I probably can skip to my summary, and there's only a few points I want you to take away from all of this, is that you shouldn't be, I hope, be afraid of astrophysical simulations. Many of the ones in terms of computational galaxy formation, galaxy evolution, really are just very efficient tools to track the inverse square law effects of gravity and, in some cases, the laws of fluid dynamics. The simulations that have been done to date do really well on large scales. When we look at the distribution of galaxies throughout the filamentary web in our simulated universes, they look really similar compared to what you actually observe in nature. So it tells you that you're getting the physics reasonably correct. When we get to individual galaxies, I think that's been where the field has been working on the last 20 years or so ago, that we still have a number of problems with having too many small satellites around. But we're getting there, and I think just over the last year, our group and a few other groups, I think we are actually getting pretty close to reality, even on some of the smaller scales. But really what the field needs now is more boundary conditions, and that is where the Gaia and Square Kilometer Array and some of these other facilities will really help. And the last point is, to take from it again, is think back to those, I spent a good 10 minutes at the very beginning showing you a number of different applications for these sorts of codes outside of astrophysics. My own students, some of them go on into academics and into astrophysics, but I've had just as many, if not more, students who have taken the skills that they've acquired doing these simulations and taken them off into other areas. So I don't set out to train astrophysicists or meteorologists, but one of them works on simulations at the Bureau of Meteorology, one worked on doing natural disaster simulations for the World Bank. The skills that you pick up doing these sorts of things are transferable. They do have real-world skills. And I think that is probably as good a place as any to end. If you do want to read a little bit more, I've got an article in Scientific American. It's a little long in the tooth now, but a lot of the basic arguments I just made in terms of the basic low-level physics is covered in the Scientific American article that I wrote with Rodrigo Ivada. And just wanted to end by saying, yes, thank you again very much for letting me talk to you tonight. I'm here for another month, but even when I'm not here, I really do like talking with folks. And if you do have any follow-up questions, and if there isn't time to do it now, really just do not hesitate. Just email me. I'm happy to chat with folks. So yeah, don't be bashful. I'm happy to follow up with you if you have any more questions. So thank you.